if this mess is only a function of x, here's an integrating factor. If this other mess is only a function of y, here's an integrating factor. But for the homework, you should be able to do it because you have the book in front of you. But I don't want people, I'm not allowing crib sheets and stuff like that on the exam, so I don't want you to memorize some wacky formulas I can't even keep in my head, okay? So there won't be one like this on the exam, but there's going to be something similar to it, which we'll get to, which will be on the exam, okay? And I'll talk about that after I do this thing, okay? So we're looking at the equation now, so let me just see what happens over here. I'm just going to do this all, because it's very straightforward, but it's messy, okay? So I have the equation m of xy dx plus n of xy dy is equal to 0, right? There's an example. We did plenty of problems last time. Okay, now, suppose we do partial m partial y, and we find that it's not equal to partial n partial x. Because this was a necessary and sufficient condition for exactness, it says that if that condition holds, that is the m dy not equal to dx, no, it's not exact. There's no function u whose total differential du is equal to that. So here's the idea of what's called the integrating factor. Maybe we can take this equation and multiply it through by some function we'll call mu of xy. I'll just use the notation that the book uses, okay? Don't confuse it with u, it's mu, the Greek mu, okay? And maybe if I choose mu, in a certain way, it'll become exact, okay? So let's just multiply through by mu, where mu is not an unknown function at this point. So I get mu of xy times m of xy dx, right? Plus, right, multiply everything by mu, of course. Mu of xy, n of xy dy is equal to 0. All I do is multiply by mu. I don't know what mu is at this point. Okay. Now, why am I doing this? Maybe I can find a function u of xy such that this new equation is exact. Well, you know the condition for exactness, right? It's still the same. Okay? Whether you call this m or mu m, it doesn't make a difference, right? So this is exact. The new equation is exact if and only if what? The partial with respect to y of the dx coefficient, which is now mu times m, equals the partial with respect to x of the dy coefficient, which is mu times m. Right? And the idea here basically, when we get a partial equation on mu, you're not going to be able to solve it, but under certain conditions we will be able to. Okay. So let's just do, and again, I'm going to do this just like we do in calculus. How do you take the derivative? It's the product rule, but for partial derivatives. So you get mu on the left, partial m of partial y, plus the partial of mu with respect to y times m, right? Mu dm dy plus mu times m. And the right-hand side, I take a partial with respect to x. So I get mu times the partial of n with respect to x, plus the partial of mu with respect to x times n. Okay, let's bring all the mu stuff on one side. Okay, so mu, remember, is a function of x and y. I don't know it at this point. I got partial m partial y, right? Bring this guy minus the partial of n with respect to x. Mu dm dy minus mu dm dx. On the right-hand side, I have n of xy, which I know, partial of mu with respect to x. I got mu, I got n d mu dx, oh sorry, minus m d mu dy. Minus m, the partial of mu with respect to y. If I can solve this for mu of xy, then I have the integrating factor. This is 10 times, 100 times more difficult than the original problem, okay? Right? We don't know, at this stage of the game, we don't know how to solve partial differential equations like this. I can do one like this, right? That's easy, right? Of course, I just integrate, right? But over here, no, this is too complicated. Okay, so at this point, basically, we say, okay, we were kind of too aggressive in what we tried to do. Let's try to simplify this as much as we can. Maybe we can get an integrating factor that's a function only of x, and that'll simplify things, okay? So what we do now, basically, is suppose, okay, that mu is just a function of x, not a function of x and y. So now, of course, the class of equations that can integrate is much smaller, but maybe there are certain equations where the integrating factor is just a function of x that I have to multiply through, and I can get things to work. Okay, so what happens now? So now I've got mu of x, that's my unknown, and now I have these two guys, partial m, partial y. I'm going to use a subscript. You've seen this before, right? It's just easier to write. Partial m, partial y is also written sometimes as big M sub y, okay? Minus partial m, partial x, okay? That's that. Now what happens on the right? If mu is only a function of x, this guy goes to 0, right? And of course, this is just n. This is the regular derivative now, because mu is only a function of x. So that becomes n, the derivative of mu with respect to x. Notice I went from partial mu partial x to the derivative of mu with respect to x, because mu is only a function of x. Okay? Okay? Okay, so we get the differential of mu over mu equals my minus nx over n. See if that's right. Right? D mu over mu. And let me just make a mistake in algebra. Yes, okay. Now, here's the problem, okay? If the right-hand side over here is a function only of x, I'm in business. It's an ordered differential equation, right? Variable separable. But if it depends upon y, my assumption is wrong. In other words, if the right-hand side here depends upon x and y, or just y, for example, then the assumption that mu equals a function of x as an integrating factor is incorrect. Remember, I said suppose. I don't know what's going to happen. So basically what happens now, if the right-hand side, which is the m dy minus the m dx over n, is only a function of x, well, then I'm in business, right? You know how to do that, right? I integrate. There should be a dx over here. Okay. Now I integrate on the left and the right. On the left-hand side, I've got the log base c of mu. And this becomes the integral now of m sub y minus n sub x over n dx. And this integral is integral as you did in calculus. It's not a partial integral like we did over here, where we integrated partial with respect to x. Okay? This only makes sense now if the right-hand side is only a function of x. Then, of course, the integrating factor mu is given by the exponential of this expression. And you see now why I'm not holding you responsible, to memorize this so it's in my head, right? Okay, so you start off with m of x y dx plus n of x y dy equals 0. You hope it's exact, but it's not because it failed this test, okay? Then we can get an integrating factor, which is a function of x, given by this formula, provided what? Provided that this guy over here, the integrand, is only a function of x. Okay? And we can do the same thing, and we'll go through the algebra if it's only a function of y. Let me just outline what would happen over there. Okay? Now the second part of it is I'd say let mu be just a function of y. Maybe that'll work. Okay? Then what happens over here? You still have this thing on the left, and then this guy goes to 0. Then you solve du to derivative mu with respect to y. It's variable separable under the assumption that something else is only a function of y. So let me just summarize those two. Okay? And we'll just apply it. Okay? So we have this equation. So we have the equation m dx plus n dy equals 0, and assume that it's not exact. If it's exact, we know what to do, right? Okay? Then we have basically two possibilities. If the partial of m with respect to y minus the partial of n with respect to x divided by n. Remember, this is all a function of x and y, right? When we start off, it's m of xy, n of xy. So if somehow the algebra works out that this guy over here is only a function of x, okay, then the integrating factor, we can find an integrating factor, mu of x, given by the formula exponential of the integral of dm dy minus dn dx over n dx. Okay? Which means, of course, that if that condition is satisfied, this over this minus that is only a function of x. You can then calculate mu of x by this formula. If you multiply through by that thing, the equation will become exact. Okay, but that's a big restriction, right? Maybe it will work, maybe it won't work. And the other one, about integrating factors as a function of y. And the way that would go is the following. I didn't do the proof in full, but it's exactly the same. Okay, you just make mu a function of y. And then you'll find out if, now what's the condition? dn dx minus partial m partial y over m is only a function of y, then we have an integrating factor, mu of y, given by the following. It's given by the exponential of the integral of partial n partial x minus partial m partial y divided by m dy. Okay? And I can't memorize this. Okay? It's, okay? But again, you have a book, and when you're an engineer in practice or a mathematician, the advantage is you have books in front of you. So, okay. So, like I'm saying, because I'm not allowing notes and books and stuff like that, I feel it's unfair for me to make you memorize that crazy formula. Okay. But there is something related to that which I do hold responsible for, and we'll get that in a second. Okay, before we get to that, let's just do some problems that illustrate this. Okay? Oh, you took the wrong one. Okay. Let's do an example. And obviously, these things are going to magically fall into the category of what we just said. But it's, convenient. At least it'll give you some more exercises of integrating the equation. Okay? So here's the first example. Suppose I have the equation 2y squared plus 3x differential of x. Okay? So we've got 2y squared plus, sorry, a little bigger. So we've got 2y squared plus 3x dx plus 2xy dy is equal to 0. Again, so I got 2y squared plus 3x dx, and then 2xy dy equals 0. Okay? Well, this is our m of xy dx, n of xy dy. Let's see if it's exact. What's the partial of m with respect to y? I get a 4y, right? What's the partial of n with respect to x? I get 2y. 2y is not equal to 4y, not exact. Okay? Therefore, not exact. Okay. Let's see if number 1 will work. Let's take my minus nx over n. What's the m dy minus the n dx over n? Is that it? Yeah, my minus nx over n. Well, 4y, we calculated that, minus 2y, right? Divided by big M, 2y squared, is something's wrong over here.
And
It's n. It's n. Yeah.
I'll just skip.
Okay, what's our cap n in our problem? It's right at 2xy. So clearly 4y minus 2y is 2y over 2yx. That's 1 over x. Oh, wow. Okay. So what happens is that condition 1 is satisfied over there. That thing is only a function of x. So there's my integrating factor. So my mu of x, in this case integrating factor, is the exponential of the integral of that mess. Well, it's that whole thing, my minus x over n, is just 1 over x, okay? If I integrate 1 over x, I get log x, e to the log x is x, okay? So hopefully now x is an integrating factor, okay? So on exam, I may give you something, a problem like this, okay? And I'll say something like, show it's not exact. Well, all you gotta do is do these guys, right? Okay? Then I'll say, I won't say then solve it. I'll say something like, show x is an integrating factor, okay? So now what do you gotta do? Okay, so your first part is very easy. And now I'm saying show that x is an integrating factor. Well, here we know it is, but let's just do it anyway. That means when I take the original equation multiplied by x, what, it should be exact, okay? So take that integrating factor now and multiply through. What's our equation come out to be now? It becomes 2y squared x plus 3x squared dx. Haven't changed the equation at all because I'm multiplying both sides by x, right? 2y squared x plus 3x squared dx. Now what happens to this guy? 2x squared y dy is equal to 0, right? Okay? And this is our new m, let's say, and this is our new n, not to be confused with the m and n that we had before. Okay? We don't want to call these something, we call them p and q or something, I don't care, right? Now, the partial of the new m with respect to y is what? It's 4yx, right?